Hello. Hello, we are back. How did you find what Santi showed us earlier? It was really good. Plus, I have the big screen, so I was able to see the entire sequence of images and then the music. I don't know everybody else, but whenever I see something like this, I feel like I want to create something. I want to go out and program, code something. That's the feeling you get. Yes, it's like inspiring to go out and do something, anything. It was really good. So if you want to follow him, you can find him on Twitter. And we are ready to go on with our next presentation, right? Yes. Well, what can I tell you? All of the presentations have been great. And I think this one is going to be really, really interesting. I was reading a little about what we're going to be hearing about the wrong code that Federico was telling us about earlier. So we're going to have Esteban Küber with us. He is a member of the Gross Compiler
Recording
team
in progress. Recording
and
stopped.
principal engineer in Amazon.
Recording in progress.
So he's going to introduce himself before he starts his presentation, but I'm excited to hear everything he has to tell us. It's great to have you with us, Esteban. Thank you. It is my pleasure.
Should I begin? Okay. If I can get on full screen. Thank you. Good morning, good afternoon, depending on where you are. First of all, I would like to acknowledge something very bad that's happening right now from this little place that I'm standing from here today. All the victims of the war have my solidarity because war has no winners. I am Esteban Küber. As they mentioned earlier, I am a member of the Rust compiler team and principal engineer in the Rust platform team in AWS. Today, I want to talk to you about the language that does not exist, or the language that Rust isn't. I'm going to give an example of things that Rust doesn't allow and explain why. What can we do as an alternative? How would Rust look like if it allowed those things? And to speculate about the feasibility of changing language to allow it. If you're looking at this, perhaps you already have some experience with Rust. The language is famous for being hard to learn, and that's a valid observation. Learning Rust can be hard. It has a lot of new concepts, and the borrow checker rules, although they are simple when you are learning them, are a bit complex and subtle in practice. Part of this difficulty comes from the restrictions of the language itself. Rust has to provide zero-cost abstractions to achieve executables with low consumption of memory and high performance. And it also has as a goal to minimize the risk of bugs. These requirements cause the language to be more explicit than others. During this talk, I am going to jump from feature to feature that is not necessarily related to try to maintain this talk short. But if you have any questions, do not doubt to ask them, and I am going to answer them at the end, and I'm trying to keep a thread. So first of all, let's take an example of Python code. If we translate from, and it's really easy to learn, even if you do not know the language, you have an idea of what this code does. So if we translate that to Rust, the compiler is not going to be happy. This code is missing a lot of things to be valid. The arguments have to have a type. The return type, if it's not present, is the unit, so we have to have something there. And finally, to be able to print the value of the function, it has to have a type that can be printed. In the case of Rust, this is represented in the fact that the type implements the trade display. So the first thing you learn with the language is to use specific types, such as an integer of 32 bytes. So if we compare this with the Python example, it does not imply necessarily the same. This version in Rust only works with one type. Python version works with any type that's printable. On the other hand, if we have a type that can be printed in the Python version, we just find an exclusion data exception, and in Rust, that failure mode is impossible. Okay, well, it's not impossible, but it's a lot less common, and it's not going to happen in this case. But if we want the same flexibility of Python in our code, what can we do? An option is to use type parameters. And these parameters work very differently from Python, or for the same case as Java. They use a process of monomorphization. This is a very complicated word that means that the compiler checks all the uses of this function with these type parameters and creates the machine code for every combination that it sees. So it copies and pastes the same function many times, replacing the parameters with the types that were used. That makes that the executable is in general as fast as possible, but costing us more compilation time and occupying more space in the final executable. But this example code is going to fail during compilation because println is a macro, but it only works with types that implement trade display. And in this code, we do not specify that T has this restriction. We here find this situation in which Rust prefers to be explicit. Why? Because the compiler can see that all the uses of the function, of the T function, implement display and allow it. But this means that the contract of the API in the function is implicit. So changes in the body of the function can cause changes in the contract, and that the existing code stops working suddenly or allowing code that should be rejected. So this would necessarily mean that it would be evaluated of all the types, so compilation would be slower. It will also complicate good errors of compilation. These terrible errors of C++ are usually caused when you incorrectly use an API of a function that it is behind the template. Templates work in that way that I just described without extra information about restrictions. So this is why Rust requires trace values, specific annotations that restrict the types that can be used when you call a function. So with this code that you can see here, the compiler can see that the argument X is always going to argue display. So when you call the function is that you have to confirm that the argument has a type that implements display. I just mentioned in passing that this has a cost in compilation time and in space in the executable. So if we want to optimize our code in those two regards, we have to find alternatives. One of them is trade objects. If you are familiar with low-level languages, you probably know this terminology perhaps under the name of vtables or virtual tables. If you know Java, you will know that all objects except basic objects are behind virtual tables. They allow you to change implementation during execution and to have only one implementation in the algorithm while different types are ongoing. So the algorithm needs to know how to find the different methods in the virtual table. In memory, the virtual table is a pointer to the real value and another pointer to the list of all methods that this value has, with a consistent formatting that does not, and it doesn't matter the real value. So this is very flexible, but it has a cost. Now, every time that we call a method over the trade object, the executable has to go after pointers. The position of the data in memory can be anywhere, and making execution or running very slower, compilers can help turning virtual calls in the same code that would have parameters that are monomorphized, but the cost should be paid for. On the other hand, in most cases, the speed of monomorphization is not necessary, so we can use trade options. There are also restrictions of the type objects, of the trade objects, about which ones can be valid. Some that have functions that are associated, constant, which are associated, or types, which are not representable today as trade options. Each of these restrictions have the same underlying reason. How do we represent these elements in memory? With the constants, we would have some alternatives of implementation. For associated functions, we would have some possibilities. And as users, nowadays, as programmers, we can transform the associated function in a method, adding a self method that the implementation does not use. But the associated types is more complicated because any representation of the types will request to assess types during the execution time, not the compilation time, and Rust is not in conditions to do nowadays. That would be an ability that leaves more questions than answers and will require a lot of work to implement. Of course, one possibility today is to ignore the problem and to move all the types, constants, and functions to another trade to be able to use trade objects, divide the problematic trade in two and restrict those elements. Another restriction that we have when we have more than one trade, well, nowadays we don't have a way to turn a trade object that represents many trades into another trade object that only represents a subgroup. An idea that's going around is having a trade object with pointers to a specific trade object from each trade, which will allow us to go from box to foo plus bar to obtain a box foo. Given all these issues, will we want an alternative today? We have one. One of those is, and perhaps obvious, is an enum that allows us to represent this, a value that can be one and only one of these choices. This option also gives us flexibility. We can leave that function without modification, the one that we had originally, but we can implement the corresponding trade for the enum. But as you can see, it's a lot of work. We have to write a lot. And nowadays, this repetition, we can eliminate it with macros or procedural macros. But how would the language be if this pattern were easier? A proposal that's going around is to implement anonymous enums. That's to restrict the types that are accepted as arguments or returned with function with heterogeneous types. And since all available types are a closed group, that is that the compiler knows exactly what types are possible, different from trades, the compilers can automatically provide implementation of display if foo and bar implemented it. This change would not be revolutionary. None of this is very complex when implementing it, and I can bet that something similar to this will exist in the future. And if you look at the syntax that I'm proposing here, we can see that there's a direct relationship between trades and enums, algebraic groups that are open and closed. It's the same concept with different uses. If I were a gambler, which I am not, I would bet that in the future, the distinction between trade and enums are going to be minimal, and it would be easy to trade between one another. But while you're experimenting, all these details are irrelevant. Everything that you want to achieve is to explore the different designs that you can want, depending on the domain that you're working with. So that's the reason why a language such as Python, in which you have a lot of freedom to make representations, even if results in code that is less robust and hard to maintain, are so popular. So what can we do to bring Rust closer to Python? Anonymous enums wouldn't be enough, but they would work. Why wouldn't we have inference as well in the signature of functions? Well, Rust is very conservative regarding different types. So nowadays, it only works in the body of functions. We have strong rules that the language effects have to be localized. Change a portion of the code in a module should not cause an unrelated code to not work. So if we allowed inference in arguments and returns, the API that you write today could be broken very easily. And that argument is just enough to implement different types in this position, but during development would be nice. And during development, if you're working in one project, what would be the consequences of accepting inferences of type in functions if we restrict them to private functions? Well, we only affect the library that we're modifying. In our client would not be affected. Here is another place that we can make the language easier to use during development without losing the rigidity that makes us reliable in our dependencies. Changing the subject a bit, our request is to be able to use variables as enums, as types. So what we do is to create a new struct with data to the variable. But in the future, we may use the variable directly as if it was a type. This is not designed yet, but there have been internal conversations about it, and I'm convinced that at some point this will be available. And there are examples of change in that regard. The expressions let else that are only available. You can see here are a comparison between both features. They allow to clean the code a little bit from common cases. In this example, it's not too dramatic, but to delete lines of code always helps. And as a note, I have used it in the compiler, and originally I didn't think that it was very useful, but now I changed my mind. One of the cases that we see very often, and it causes confusion, is the types that represent text. I'm not going to be very detailed about this. This would be a talk in itself, but knowing that there are string slices and allocation of strings, you can make the argument that the type of string by default would have to be copy and write. So this type, by having two string slices and mutating them, it turns into an allocated string, so we must differentiate between both of them. I don't think this is a change that is going to occur in the language, because being able to identify when we are allocating memory and when we are using memory that's already allocated is important for high performance programs. But at the same time, it's very easier to turn a slice into a string to a copy and write stream. We will have the option in the future to change to copy and write string very easily. One of the advantages of the enums is that you can make pattern matching on values. Is the ability of the language that I miss the most, but it's not perfect. Pattern matching allows to extract a field that is deep between a type, beneath the type, but when we have a field that's a container, we have a problem. We cannot use pattern matching. It doesn't matter if it's box, arc, etc. Nowadays, what you do is write more code and let it work. Innately, with the box type in particular, there is a special syntax, and I have used it in the compiler. It's very useful, but it does not have a stabilization path right now. However, there's a project to allow pattern matching to take advantage of Autodraf in all the container types, or at least those from the standard library that have been opted in. The syntax is not finished yet, but it's probably there won't be new syntax, just more code is going to work. And if you are accustomed to an object-oriented language, the second question that you made when you started programming in Rust, how do I determine heritage? Well, Rust does not support inheritance, or it just says, what, am I being loaded? Well, it's not that, it's not a joke. Rust does not support inheritances. This is the problem that I'm going to mention is the diamond problem, because if they inherit, they have a lot of paths to the same origin. They have a strict algorithm for the superclass members, and other force you to specify the path to specify the superclass when the case is ambiguous, or just not allow you to have a class to other classes. So you can imagine the following syntax, but it does not exist. Rust does not have this. Beyond what the language allows, the experience through time has suggested that you can choose composition instead of inheritance, because it causes less headaches when we maintain our software. Rust does not give us that alternative to use inheritances, but composition is always available when we put the superclass in a field. But without language support, every time we want to call the X method, we would need to specify the full path. This example cannot be too upsetting, but because there are two levels, but on the long run, it becomes upsetting and hard to use as your code becomes more complex. Here is where the language capabilities that already exist can help us. So if you ever ask yourself if the string slice method are available in a string type value, it's probable that you may have learned this self-reference. So in each expression that we have access to a field or a method of a value, the compiler is going to try to find it over the corresponding type. But if it doesn't find it, it's going to try to add or remove borrowings. And the compiler is going to try to use all the implementations of deref on that type. Deref is a trait that allows us to tell the compiler that if you have an expression in which you are using methods and types and they are not present, but those are present in type B, then use those. This is very useful when we want to abstract a little bit with which type are we interacting without making specific or costly conversions. That's the reason why borrowing from a heap allocated string does not turn into a string slice. So it allows us to emulate the experience of inheriting. So if you implement the ref for the extract foo and bar that returns foo, we can use it instead of in the original way. We can change this with this. So if you see the last line, you don't have to know that I'm going through foo. So doing this is not necessarily idiomatic and does not allow us to replace the function from the fake superclass, but that does not eliminate the usefulness of this pattern. Of course, with traits, we also have other ways to represent dependencies with supertrade. This is similar as inheriting functions in other languages, but we are not inheriting. This is an assertion that B is implemented over something that A implements as well. A very personal case is that of iterators. Do not try to read this. It's an implementation of a problem from a brain teaser that's using Rust, but it's very representative of the state machine that you have to write an iterator by hand. It's easy to make mistakes. So I'm convinced that in the next year, we are going to be able to use translators to write iterators implicitly. And it's similar to what you would do in Python. This code is equivalent to the previous one. It's exactly the same, and they compile to the same. And to close, I would like to talk about clone. When we call clone, we are constantly reminding ourselves that we are copying memory. And that is the origin of a lot of problems that when people with experience start learning Rust, because we can try to eliminate unnecessary clone. But clone has nothing to do with efficiency. A very small type can implement clone with a very similar cost to copy, and a big type can implement copy and be a performance issue. So the idea that clone is inherently inefficient is not correct. What I can imagine in the future is a new trait that allows the compiler to know that if our type is not copy, because you can create a new value just copying the bytes in memory, that the implementation of clone is cost effective. So that would allow us to interact with Arc, for example, without thinking about cloning. So if Rust called clone automatically, these container types may impose the requirements in which if you clone too much, unconsciously perhaps, you may cause bugs, especially in multi-threaded code. So this is one of the cases in which I am unsure, but I think that in the next 2 editions, we can get to change the language to rote clone less. So now to close, I just showed screenshots from different parts of the language, which you probably knew some of them, but perhaps they gave you some hope that perhaps these features can be brought down a bit, and that now you may know what to do to avoid them. Thank you very much for your time. I do not know if there are any questions. Thank you so much. From what I see in the matrix, there's nothing yet, but if you do not mind, while we wait, in case someone writes a question. So if you had infinite resources and the equipment and everything, what would be the first thing that you would take and fix? It's funny because it's something that I didn't mention in the talk. If I could just throw resources magically, probably what I would try to do is helping MATLAB and all the people that are working at Rust Analyzer to achieve parity in the way that we show errors, because the compilers, when you call it from the terminal, there is a lot of effort that it looks somewhat understandable regardless of your experience level. But in Rust Analyzer, which makes an impressive effort to be useful, unfortunately, presentation is not the same quality nowadays. And part of that is the APIs provided by Visual Studio Code. They do not allow us to do it. There are some alternatives that I've explored, but they would imply a lot of work to be able to have it. So that would be the first thing that I would like to do. That the experience in ID is even better than what it is in the terminal. So, and also things such as making the compiler stateful, meaning that it has memory. So if you're calling the compiler constantly and we are just going in circles, the compiler can detect that and tell you, here, look here, you're just trying the same thing all over and over, maybe try something else. Yeah, exactly that. Yeah, I think that that is one of the things that we can do. And there are a lot of ideas. For example, if a compilation error occurs within a test, try to recover and run the test and show the test values in the error, for example. So there are a lot of things, beautiful things that we can do, but there are very large efforts. And if it's not much to ask, all of these ideas, are they documented? Or are just ideas that the community has and then they talk about it, but they are not documented yet? Well, it depends on the idea. One of the places where you are going to find, if you're interested in being part of this conversation, one of the places where you're going to go and listen what people are thinking about is go to internals.rustlang.org. That website is where most of the conversation happens before there is a request for comment. By the time that an error is created, there is already a lot of previous work and there have been a lot of conversations. And those conversations also occur in Shulip among people who are part of the different teams. Because we have the compiler and the compiler team, but we have working groups which are specific for different things. For example, there is a working group for sync. So we have a group of people that's dedicated to trying to use async in Rust is the best that you can do. We know that it isn't today, but we're trying to improve every time incrementally. And other conversations are also going on in conferences such as these, in chats, in the hallways. Perhaps somebody has an idea and it's just going around in somebody else's head, and then it appears later, 6 months later, with solutions for some of the problems that were identified. So it's very organic, but I insist, if someone who's listening to this wants to be part of this internal conversations, internals.rustlang.org, and the Sulip chat of RustLang. Those two places are very good places to start. So can you do me a giant favor? Are you on Twitter? Yes, I am. Can you please tweet this? Because with the conference account, we can retweet this. And if someone who's watching is just inspired to see you, and well, I had this idea for months and I want to share it. So my idea is to take any idea to evolve the language. Taking it to those two languages to those two places is the best idea to get it to people who think like you and to receive feedback about what could you have missed? Because you are sometimes thinking that you are planning for months and somebody else tells you, yeah, do you know that already exists? Yeah, that happens. Well, thank you so much. I really appreciate that you came here and that you're here with us. I assume that people can reach you through Twitter and the conference chat. Yeah, my Twitter handle is EKUBER. And I am available at any time for any question that you have. Thank you so much. Thank you.